All right, perfect. So yeah, nanofibers for energy application, right? So basically, we're going to talk about the basics and what type of work can be done in this application field. So let's go on to the next slide. Let's go. Yeah. Okay. So let's move on to the next slide. Let's see if we can move on. All right.
Okay, so before we just start the energy field, I just wanted to briefly give you details about our company as Innoven. So what we offer in terms of, electrospinning and nanofiber based products. So as Innoven, so we've been in this sector for 12 years and we are actually providing solutions for, electrospinning technology. We are producing machinery from lab scale to industrial scale, and apart from that, we are offering R&D services, which can cover proof of concept, contract development, of course, as well as, the feasibility studies at the early ages.
Right.
So right now, I just wanted to, give you a little bit details about the nanofiber market. I believe you are seeing the screen right now. Yeah. As you can see, this is a market report. Actually, this is a very good market report that is actually available online. You will see that this nanofiber market is going to be grown in actually by 2028 by 26.1%. So this is a very big amount. And as you can see, there are three major application areas, from filtration, medicine, and also energy. So energy field is very popular and it is going to be very growing by 2028. So this field is very, very important for that. So we can come up to the next slide. So as you can see here is actually the number of scientific publications actually for energy field. Only you see that from 1999 till 2021, this actually article publishment rates are growing rapidly, and you see that last year it is 9,648 articles only for energy applications. So this is a very, very important field, and as actually nanofiber based products, you will see, of course, in more detail in upcoming slides, and of course our guests will be giving us more details as well. But this field is very important for our technology. So we can come up to the next slide.
Right. So thank you, Bushra. So we're going to now talk about the technical aspects, what type of research is going on. It's important to note that most of this information and most of this progress we're making so far in science and academia today is that it's still in the research phases, but you were able to see that it's actually increasing exponentially, the interest, and it's high chances in the future that we'll be seeing a product out of these energy-based nanofibers soon because of their unique properties. So let's move on to the next slide. Okay, so yeah, so we're going to talk about the general, overview of energy and nanomaterials. So yeah, we're talking about electrospinning to produce these nanofibers, what type of applications we can use for like allowing these specific research fields to advance and help the industry towards energy, and large scale electrospinning can be achieved with the technology of open surface that we mentioned before. So let's move on to the next slide. Right. So just before I begin, I want to give very, very basic definitions. So yeah, we're talking about nanofibers, which are essentially one-dimensional nanostructures. They have very unique and very special key properties that allow them to be applied in this energy field beneficially. For example, their porosity, they have large surface area to volume ratio, and they have, of course, sub-micron fiber diameter ranges. So electrospinning is the process to produce these nanofibers, and we're going to talk about how they relate or pertain to energy industries. So let's move on to the next slide. So yeah, type of applications, a small general overview of what you'll find in academia right now is like solar cells, nano generators, lithium batteries, and a couple more of the fields that are being worked on. So let's move on to the next slide. Okay, so yeah, solar cells. So as you know, solar energy is renewable energy, and people are really looking into having more improved solar cells. And nanofibers look to be promising materials. mainly because of the large contact points. So they have perhaps better interaction with absorption of light and for energy conversion. So people are working in working about it today with composite nanofibers, and it might also be essentially, if we're able to get a working prototype, if somewhere in industry we're getting prototype, we'll be able to get a cost-effective way of producing solar cells, because electrospinning itself is cost-effective. So let's move on to the next slide. Another, like one of example is that with nano generators, these are essentially piezoelectric material media that take mechanical energy and convert it to electrical. In the case of piezo, you would apply pressure, and you can produce this with electrospun media. They're being used or you can read about them in research articles today. So here it's more so a case of electrospinning rather than spinning. PVDF, is a well-known electrospinnable polymer, but if you were to electrospray with the key particles like silver or graphene, you will effectively increase its electronic activity. And doing so, when you are applying pressure, you can also increase or decrease the energy of electrical energy, and you can use these in sensors. So let's move on to the next slide. Okay, lithium batteries is something that we're actually trying to get into more. So it's essentially electrospun media used for lithium battery anodes and lithium battery separators. So they're suitable candidates because of their conductivity, porosity, surface area. I'll get into more information about this later, but this is essentially people are looking into producing generally battery media for with electrospun fibers as the next generation for these materials. So let's move on to the next slide. These are other examples. Fuel cells are similar to the batteries, except they're exerting some energy from the fuel. Supercapacitors being these high electrochemical storage devices using carbon material, and you can always electrospin carbon-rich polymers with electrospinning. So these are something that some works are also being or basically being researched upon. So let's move on to the next slide. Okay, so these are the advantages of nanofibers, as I mentioned before: high surface area, small fiber diameters, high porosity, low cost of production versatility. These are just generic. For lithium batteries, we will talk more in depth later on, but all of these essentially help ion conduction or transfer of electrons, nanomaterial media. So these are just key properties of what you might look at for your nanofiber media, and how they can be applied for energy-based devices. So let's move on to the next slide. Yeah, so this is a stream spinner. It's the open surface industrial machine. So mostly what you would have is, if you have a ready prototype and you want to upscale that, you would normally have to use similar machines like the ones behind me to produce a continuous R2R system production, and that you can essentially commercialize for nanofiber based machine. So it has high production rate and it's compatible. It's basically a patent pending technology at Innovent. So let's move on to the next slide. So yeah, this is a stream spinner. There's essentially a module that you can control the homogeneity, or rather you can estimate or measure, you can examine your media as it's being made in real time. Like if you're producing a nanofiber layer and you want to understand how well it's the production is, how consistent the production is, we have a quality control system that essentially is a suction air that basically can measure the air pressure and see how well it's being uniformly distributed. So let's move on to the next slide. This is a small video of how it works in action. We'll just cut it short. So let's see if we can play it with the audio off, if possible. Yeah, so all right. So yeah, this is the air pressure testing. So what you see here is that there's a roll-to-roll system. This has recently been electrospun, and when it gets electrospun, it reaches one end, and it reaches this module here that I mentioned before. So this module has a lateral motion moving to and fro. There's pressure being applied on it, and what's happening is that you're measuring its, it's basically its pressure difference, and that way we're able to estimate, okay, the electrospun that media that we synthesized, how consistent is it? So it's like basically a test of how it works. So that's enough. So we can move on to the next slide. So yeah, my colleague mentioned, what we've done before. We can do R&D. We can basically do contract manufacturing. of these media if you need, and these are other related, potential related capabilities on our side. If you have any interest, or if you're looking to work in this sort of type of field, or you already have and you would like to have some sort of assistance or partnership, you can reach us at sales@innovencer.com, or you can enter our main website. All right, so let's move on to the next slide. Yeah, this is a contract manufacturing service I mentioned before. So whatever you have, whatever you need, like, we can tailor it and make a production demand based on what you're looking for in a like per production demand or time. So let's move on to the next slide. All right, so this basically gives a conclusion of the R&D that the increase of R&D of electrospinning can be attributed, okay, and we can increase the applications if needed. And just to give you a small understanding of how it looks like, the media is essentially in this form. This, what we have here, is spun. We have essentially spun media. Let's see if we can get a better view at that. Right. So it's basically flat shaped media in use for this right now. Here it's PVDF and blend of 60 micron with TPU. What we're working here essentially is let's see if. Yeah. All right. It's great. All right. So yeah, this is essentially spun on some sort of substrate. Doesn't matter. You can just take it out. It has to have a specific idea. We'll talk about how we worked with it before and our progress so far. Let's move on to the next slide. Right. So moving on. Right. All right. So yeah, this is what we were talking about. So essentially, the material has to have a specific thermal stability, and it needs to basically. So we're using electrically conductive polymers like PANI, polyamide is also good. PVDF is also good. However, PVDF has an issue with crystallinity, so it might prevent or inhibit lithium ion transfer. So that's something you have to look into. So we've produced these membrane media, and right now we're at a stage of trying to test its basically in a pouch cell device, and we're right now talking and looking for stuff. So this is basically our progress so far. We hope to, and we intend to actually advance this field too further, so that we can have a fully developed battery separator media for this device. So let's just conclude with the next slide. All right, so thank you very much. This basically covers the general overview of energy-related nanofiber applications. If you have any questions, I welcome them.
Thank you so much, Amar. So if you have any questions, you can type down actually in the chat section of YouTube, so we can address it during our presentations. So right now we would like to welcome Ms. Begüm again, and we would be happy to have her presentation right now. So Ms. Begüm, the floor is yours. Thanks a lot for joining actually for this webinar.
Thank you so much, Bushra. Could you please make me co-host?
Yeah, sure. We are just working on it. We will give you access. Okay. So my friend is just going to give you permission for screen sharing, Ms. Begüm.
I couldn't do it.
Okay, I believe we are.
Yeah, she's there.
Okay. They're just handling it. Okay, can you please try it again, Ms. Begüm, if it's possible?
Yes.
Perfect. Thank you so much.
Okay, wait a minute. Is it okay now?
Yeah, we can see it.
Yes. Okay. Good afternoon, everyone. My name is Begüm Yarar Kaplan. I'm a researcher at Sabancı University Nanotechnology Research and Application Center since 2018. My study is mostly focused on electrospun materials for energy storage and conversion applications. Today, I'm going to shortly talk about electrospun membranes and electrode for fuel cells and electrodes for especially for the lithium-ion batteries. Okay, Bushra actually summarized it, but I would like to mention about that again. As you know, recently electrospinning has drawn great attention due to its unique characteristic, such as the continuous nanofiber network and high surface area, high porosity, and so on. And we can use this type of materials for fuel cells, solar cells, lithium-ion batteries, lithium sulfur batteries, supercapacitor, and so on. And in this system, we have several process variables. Actually, we are dividing this process variables in two. One is electrospinning setup parameters, and the other one is solution parameters. Here, the apply voltage, the syringe to collector distance, solution flow rate, and the humidity, relative humidity of the system is really important to obtain promising nanofiber mat or nanofiber structure. The other one is solution parameters. You know, this is really important actually if you are adding additional particles such as carbon or active material or catalyst into your nanofiber structure. The concentration of the polymer solution is really important here. The solvent type is really important because evaporation rate is really important when you are doing the electrospinning. And as I mentioned to you before, the solid solvent ratio is really important if you are doing polymer particle electrospinning. Okay, what we can obtain from this electrospinning setup in the energy application, we can create a nanofiber hybrid composite membranes and electrodes by polymer or polymer particle electrospinning. Actually, we are conducting polymer electrospinning for the membrane part, and we are using polymer particle electrospinning for the electrode research. Okay, first of all, I would like to shortly give information about what's fuel cell. Here is the general schematic of the fuel cell system. Here is the MEA structure, membrane electrode assembly structure. What's happening here? We are using hydrogen as a fuel, oxygen or air as a oxidant gas. Hydrogen comes here to the anode. Hydrogen come to the system from the anode side, and it's oxidized to the hydrogen ions. These hydrogen ions, you know, moves through the proton conductive membrane. In general, we are using Nafion as a proton conductive membrane here, and it reaches to the cathode. It reacts with the oxygen and water produced from this system. This is really clean system to produce energy. So we can produce nanofiber-based both electrodes and membranes for the fuel cell application. I will show what we are doing in our research group for the both electrospun membrane and electrode development part. The first one is we are developing electrospun hybrid membranes for low humidity operation of the PEM fuel cells. Here is the one example of the SEM image of the nanofiber structure. The other one is actually the other project is dual fiber-based electrospun anion exchange membranes for fuel cells. We are using the double-sided electrospinning setup. We are using PVDF and ionomer solution from the one side, and we are using PVDF grafted vinyl benzyl chloride solution from the other side, and we are producing composite membranes at the end of this electrospinning process. Okay. I would like to give more detail about the first example. In this study, we produced hybrid membranes with using sulfonated silica ionomer or functional additive with using, and we also use polymers PVDF and PVDF TRFE copolymer as a carrier polymer in the system. Why we are using actually this carrier polymer, this inert polymer provide us higher mechanical strength and control swelling under fully humidified conditions. For the first time in literature, we use this copolymer to fabrication or development of the membranes for PEM fuel cell application. You can see the general procedure, experimental procedure here. We bought this machine, electrospinning machine from the Innovenso. Here, actually, this is a really compact system, starter kit system. It's, it includes both syringe pump and high voltage source together in this system. And we use rotating drum collector to control the thickness of the obtained membrane. Actually, the final products after electrospinning is matte. Why I'm calling this matte? This product, the final product is matte because it's porous. For the fuel cell application, we cannot use this porous electrospun matte, so we are converting this porous matte to the membrane with using hot press and annealing steps, and we eliminate the hydrogen crossover in the fuel cell testing and fuel cell application. Okay, after obtaining these membranes, we perform several experiments. I'm not going to go in deep with the results, but I would like to show the hybrid membranes shows very promising proton conductivity, water uptake, and Young modulus. I would like to say that. Okay, I would like to show a little bit more about the second project. In the second project, we synthesized the anion exchange polymer with using radiation-induced grafting, and after we synthesize the anion exchange polymer, we combine it with the inert polymer PVDF, and we use this double-sided electrospinning setup, and we obtain dual fiber-based electrospun mat. Here is the content of the obtained membranes. Again, similarly in the previous study, we convert this electrospun mats to the dense membranes with hot pressing and annealing steps, and then we characterize all of them. I would like to talk shortly about the electrodes for the fuel cells. It's different from the membrane part because we have here 4 components. We have ionomer, solvent, catalyst, and inert polymer. Catalyst here we use platinum carbon. Catalyst here you can see the structure of the electrodes. We obtain electrodes. We didn't perform any hot pressing because we really need high porosity and high surface area for the electrode fabrication to eliminate the mass transport losses, and to reduce the platinum amount inside the electrode with using this high surface area. You can see the schematic of the electrode spinning setup also. Okay, as you can see here, actually we didn't use Nafion solution here in the electrode structure. We use sulfonated silica to provide better water retention ability to the electrode, and we perform fuel cell test at both fully humidified and partially humidified conditions. As you can see here, the electrodes show very promising fuel cell results with using very low amount of platinum, and the obtained power output also promising at partial humidified conditions. And also these electrodes shows very the excellent remarkable durability after platinum dissolution accelerated the stress test. The power density loss at maximum power output is around 1%. Okay, the last topic is lithium-ion battery electrodes, electrospun electrodes. Here again, we use the same system. As you can see here, we use a rotating drum collector, and we use this the same electrospinning setup. And actually, we are developing electrodes, both anode and cathode electrospun electrodes for the lithium-ion batteries. But today I'm shortly talk about the anodes for the lithium-ion batteries. Electrospun anodes for the lithium-ion batteries. These methods provide us homogeneous electrospun matte production, and it's, we can create nanofiber-based electrode by polymer particle electrospinning. What are the advantages of the electrospun electrodes? We know this 3D electrode structures provide us higher aerial contact between the electrolyte and the active material, as you can see here, and it provides easy lithium-ion transport using this intra and interfibrous voids in the electrode structure, and it provides better gravimetric and aerial capacity. And actually the most important advantage for me, it gives the ability of to obtain freestanding electrodes, flexible electrodes, and it eliminate the use of current collector with this unique flexible structure. The procedure is same with the electrodes for the PEM fuel cells. We are preparing a polymer solution, and we are preparing a solid dispersion, and we are mixing it, and we are directly electrospinning it. Okay, first of all, we are electrospinning the inks, and we obtain this flexible electrode, and then we prepared a lithium cell. This lithium cell, we didn't use any current collector. This is this is gives the opportunity of the lighter lithium-ion battery design, and we use this cell for the further tests. So you can see this in the anode study. We use anatase PEDOT-PSS based materials, and also we use carbon black in this structure. As you can see here, we obtain really good particle distribution along the nanofibers, and as you can see here, we obtain really good anatase distribution along these nanofibers. And as you can imagine, it's really hard to obtain these nanofibers. We optimize lots of electrospinning parameters. As you can see here, this red part shows us the optimum conditions for the electrospinning, this to obtain this nanofiber structures. And then we perform capacity tests and electrochemical tests, As you can see here, by means of the electrospinning method, it's possible to produce electrodes of, desired thickness or the capacity according to your needs of your battery. And as you can see here, thick electrodes shows better lithium-ion battery capacity here. Also, as you can see here, the grammatic capacity results compared to literature and LTO-based anodes. Here in our work, we obtain very promising and better grammatic capacity, and we published this study in the ACS Applied Energy Materials, and it's selected as a cover image. Okay, first of all, I would like to thank you for your attendance. Also, I would like to say, I would like to thank TÜBİTAK for their funding. Here is the project numbers. I would like to thank my PhD student and also my colleagues, Professor Selmi Alkan Gürsel and Professors Alp Begüm, and for their collaboration, and all Sabancı University Energy Storage and Conversion Research Group. Thank you for your attention.
Ms. Begüm, thanks a lot for this informative presentation. It was a very good presentation. If our audiences, if they would like to know more, please check out Ms. Begüm's articles, like publishments, her actually Google Scholar.
Google Scholars, yeah. And if anyone has any questions about the presentations, you're welcome to ask Ms. Begüm right now.
We're just gonna wait a couple of minutes if there are any more questions. So if not, then we can proceed further.
Ms. Begüm, actually, I have a question, if that's okay.
Okay.
So regarding your fuel cell synthesizing, you mentioned that you are using annealing, or rather using a post-heating process, right? For the fiber stuff.
Process is not, this means not pyrolysis. It's mild conditions.
Right.
And we are applying, we are doing hot pressing.
Hot pressing, right.
And then we are making it compact structure.
So
it's a general procedure for the electrospun membrane production.
Right. So, and you mentioned.
Okay.
I'm so sorry. So you mentioned that the main purpose is to reduce the porosity of the membrane.
Yes,
medium?
to make it compact. We are using two different polymers inside this structure. Right. So electrospinning gives us to better distribution these two components, and then the better distribution of the charged groups, and then we are making compact. Otherwise, hydrogen crossed over to the cathode side and it cannot react with the oxygen. Right. Hydrogen ion cannot produce. This is the case for the fuel cell membrane part.
It's very interesting. I was actually wondering if the heating also is adding towards increasing the electrochemical stability, or maybe the mechanical properties of your fibers.
Yes, also, yes.
Oh, perfect. Thank you so much.
Thank you.
Right. So I guess if there are no any other questions, I think we can move on to Mr. Hugo's presentation. So
thank you so much again, Ms. Begüm. So we would. There's one question.
Okay, let's see it.
Okay. So let's see. Did you need any annealing process during anode production?
No. Actually, I would like to, this is a good question, because if you look at the literature, every time in the traditional electrospinning, electrospun electrode structure, researchers mostly adding pyrolysis or carbonization step at the end. Here, we are not using any carbonization or the pyrolysis at the end of the electrospinning. We are directly use it because we need flexible electrodes, and that's why we didn't do it, and we use really high amount of carbon and active material inside our electrode structure to obtain promising lithium-ion battery capacity and cyclability.
Okay.
So, Ms. Begüm, thank you. We have another question. Why you make hot press and annealing after making electrospinning, and does this destroy nanofibers?
Actually, we are not melting it. We are pressing it to, we are sticking all of them together. Otherwise, as I said you before, for the fuel cell application, PEM fuel cell application, if hydrogen, goes to the cathode side without, any electrochemical reaction, or in other words, if hydrogen oxidation reaction cannot place, it will not work. So porosity, we need to eliminate the porosity for the fuel cell application, for the membrane part.
Ms. Betul, I'm actually this actually makes me a little bit more interested. So when you use the heating and reducing porosity, did you make measurements?
Actually, not reducing. We need to block all the pores.
All the pores. I see that. This is what I was asking. How far the factor of reducing porosity is? Like how do you completely eradicate the pores, or
Actually, we are checking it before making fuel cell test. We are performing linear sweep voltammetry, and we check the hydrogen crossover occurred or not occurred. We decide this membrane is okay after this this electrochemical characterization. Then if it is okay, if we don't have any hydrogen crossover, okay, we said it, we can use it, and we are going to test it in the fuel cell machine.
Okay, thank you.
Thank you. I believe we do not have any further questions, Ms. Begüm. Thanks a lot for answering these questions, and we can welcome Mr. Yohanes for his presentation right now. Thank you. Mr. Yohanes, welcome. Can you hear us?
Yes, I can.
Perfect. Thanks a lot for joining our demo, and we really appreciate your acceptance for this webinar. The floor is yours, sir. You can, definitely start your presentation. Thanks a lot.
Okay. I will share my presentation first.
Sure.
Yeah, I believe you can see that now.
Yeah, we can see.
Yeah. Okay. Imagine a world that is powered by wind and solar. And actually, it's not so far that most people think. And I'm Yohanes Hugo from Lstore, and my colleague and I are working toward this idea to turn this imagination into reality. Can go next. Yes. Okay. Yeah. So Lstore, we are launching a technology based on flow battery. So it's a large scale and stationary application. So we identified currently that we can combine our technology together with a large PV and wind. We can also still substitute the big power plants in the long term. And we also have a special technology because we're using hydrogen. And in the world, especially in the Netherlands, we are really strong with gas technology. And we have a lot of hydrogen infrastructure. And our technology is really fit into this idea. We also produce a modular product. Yeah, so it's based on a platform. And our customer can buy a multiple platform to match to their demand. And this technology already patented worldwide also. So let's see together our technology. Yes, the technology is based on hydrogen bromine flow batteries, and we also try to map out most of electricity storage that's available in the market, and we identified ourselves as a low-cost solution and relatively high energy efficiency. And as you can see in the picture in the middle, this is our flow battery stack. Yeah, and you can see our first but a large size demonstration in a container size on your right. And this technology that we see that we develop currently is to enable the grid stabilization in solar wind field as a co-location. So we identified ourselves perfectly matched to the world changing need. So if you think that wind and solar, they're already here, and the cost is relatively low and even lower than a coal-fired power plant. And but then this electricity, green electricity, also brings some issue into the grid system because it's intermittency. And we see that there's growing needs for storage in the large capacity versus its power. Maybe I would like to touch a bit more here because there's a lot of confusion. The power is the rating or like the supply of electricity at that moment, but then the energy that is consumed actually is in the megawatt hour scale. So megawatt versus the megawatt hour. And this is different compared to a conventional battery, where the power normally scales with the energy. For example, like a lithium-ion battery, the power is relatively cheap for lithium-ion, but because it constrained by the energy, then the energy becoming the bottleneck, and also the parameter determination for the lithium-ion cost. However, our system can be developed such as that we have the best of both worlds, any desired combination of power and energy. And yeah, we have like a product strategy here at Lstore that currently we are developing like a joint development product together with our strategic partner for 10 hours storage duration. And this is already fit for the demonstration of our technology proof of concept. But then next year, we would like to deploy our first commercial product that have the duration between 20 to 50 hours. And this is where the need for the co-location system of wind and solar to balance the energy that coming from the wind and solar. But then in the future, this is where we see the ultimate goal or a flow battery technology, which is long duration flow battery technology. And this is, we patent this technology, not a general idea, but the right way to do this long duration integrated with the hydrogen infrastructure. So as you can see in this picture, where we have the membrane stacks that producing the power in and out, and we have on the cathode side the catholyte, which is the the bromine electrolyte on one side. But from the hydrogen, we don't need to invest in separate hydrogen tank, but then we can connect it into the hydrogen infrastructure. And then we also envision that hydrogen infrastructure will be powered by the green hydrogen coming from electrolyzer. And therefore, we can store a long duration, like high capacity of energy in a cost-effective way. And yeah, maybe some of us has a question, how long is the long duration electricity storage? And it was a question for us, but after doing some analysis that we can see that when we have like a small electricity storage, then there's a lot of capex for the wind and solar to stabilize the grid to have 99.98% reliability. But then as we go to a longer storage duration, then this wind and solar becoming less and less. But then the capex for the flow battery will increase. And we find the optimum is somewhere in the middle, which is 100 hour storage time. So this is also the product that we are developing, also to integrate this technology into hydrogen infrastructure in Europe, but all over the globe also later on. And I would like to shift the gear a little bit here to go back to the science. Yeah, what is a hydrogen bromine flow battery? So basically, it's electrolyzer and fuel cell combined together. And our previous presenter, Ms. Begüm, thanks for the explanation. Already explained us about PEM fuel cell. And this is really similar technology, but we just substitute the oxygen and then exchange it with a bromine. And during the fuel cell mode, when the system deliver energy and power, we react hydrogen and bromine into creating HBr and electricity. And then this reaction is relatively spontaneous. So it creates some electricity. But when we would like to charge the battery, because we have a surplus of energy, then we use this extra energy to split the HBr back to hydrogen and bromine. Therefore, it's also called reversible fuel cell. And the schematic of the hydrogen bromine flow cell, can see it in the picture on the left, which on the first part, the cathode, we have the electrolyte side, electrolyte tank first, which contain bromine, HBr, and mainly water. Yeah, and we also have the bromine electrode location for this bromine to react. Yeah, and because bromine is highly reactive, we only need a carbon porous media. And on the other side, we have on the anode, we have the hydrogen tank, and to split the hydrogen into protons, we require catalyst. And this side is really similar with the fuel cell technology, where platinum-based catalyst is being used here. And in the middle, the heart of the cell, or the heart of the technology, is the membrane. Yeah, and this membrane function is to separate physically the bromine electrolyte from the hydrogen, but still allowing the protons to move one to another. And this membrane, as we know, have a trade-off. And the goal is to move the trade-off into favorable position. And the trade-off is between the conductivity, how fast the proton can transport from one side to the other. On the other side, how selective it is to prevent the hydrogen gas to cross to the liquid side, and also how selective the membrane to prevent the bromine species to move to the gas side. And we need to improve the membrane further and further. Therefore, we have a product that is commercially available. Maybe like one step back, I would like also to explain why at the beginning I mentioned that our power and capacity can be separated, because normally in a conventional battery, for example, like lithium ion battery, where we are familiar, where we have it also in our pocket, in our phone, the electrode, like the solid electrode, is also the reactive materials. So like the bigger the electrode, the more power, but also the more energy it can store. But then in our case, our electrode is an inert, and the reactive materials is present in form in a form of flowing media, the bromine electrolyte and the hydrogen. And then our electrode is just location for the reaction, electrochemical reaction to take place. So the membrane surface area will determine the power, or also including the electrode area, while the capacity will be determined by the volume of our tank, both the hydrogen and the bromine electrolyte. And in the case of our ultimate goal, where we are connected to the hydrogen infrastructure, so the limiting factor only will be the electrolyte tank. Yeah. And as I mentioned, membrane is like the heart of the technology, and it's really important for the commerciality of our product. And we always try to innovate in this important component. And I also did my PhD a few years back, especially looking at this membrane. And for your information, and it's the same also for PEM fuel cell. The benchmark membrane is based on fluorinated perfluorosulfonic acid membrane. And this membrane is really superior because this distinguished separation between the hydrophobic backbone and the hydrophilic functional group. Yeah. And the characteristic is that the conductivity of this membrane is really high. But because of these really hydrophobic channels that present, it also attract a lot of water molecule and make the membrane pathways wider. Therefore, the bromine species can go through to the other side, to the gas side, and we don't want this. And the idea in my PhD study is to create high charge density reinforced fluorinated type membrane, where it's basically a composite membranes, the mix between the PFSA and non-conductive polymer. Therefore, the non-conductive polymer can constrain the PFSA mechanically. So when it in touch with water, it will not swell as much as a normal PFSA. Therefore, we can still have like a very high conductivity while blocking the bromine species to the other side. And from this idea, we figure out that we can realize this and move to the proof of concept with electrospinning technique. And again, I need to thank the Miss Begüm to explain already very nicely how to produce this type of electrospoon membrane, where we electrospoon a mat and then we process it with a hot pressing process into a dense membrane. And this is what I did also a few years back, and I already tested also in a coin cell that already show like really good performance, very stable, what we are looking for over 2 months period of operation. And now I mean Lstore and Innovenso will try to commercialize this idea. Yeah. And I also would like to speak a little bit more. Yeah, what is the addressable market here? Not only for our battery, but also for the membrane production. So as I mentioned, the wind and solar is it's really cheap energy source. It's already cheaper than the coal-fired power plant. And if we also have a low-cost way to store electricity, then we really have technology that can replace the fossil-based economy. And we really see there's this need of the energy storage system to also contribute to the electrification of our total energy system. And this is like currently very small addressable market, but then a huge potential. Therefore, we see like plus 50% of CAGR, utility scale of storage. It means the industry will grow more than 50% every year. Until when? Is until that we see we reach a size of 500 terawatt hour. And maybe we ask currently what is the current stage of technology. I think we are only like a 1 or 2 gigawatt hour like globally in the world. And if we are able to address this with a flow battery technology, I'm estimating that at least we require 2 billion meter square membrane area to fulfill this need. And this membrane also need to be replaced once in every 10 years. So it's also very sustainable business. And for this purpose and to reach this addressable market of 500 terawatt hour, we are looking to have a platform of a bidirectional power plant. As you can see on the right, this is like a schematic, how it looks like with like a human scale located here. And this is like a 1 gigawatt and 100 hour storage time. And then this is one platform. And then if it's needed, that we can install multiple platform in the same location. Yeah, and it's not like a lithium ion that have like high fire hazard that it need to be put separately. We can really put our technology side by side. So the footprint actually relatively very small. Yeah. So it's really easily like all the coal-fired power plant here in the world, we can just replace it with the flow battery product, and we can really move toward the green energy transition. And yeah, this is also like a lot of question that we receive. What is the market acceptance of like hydrogen and bromine with hydrogen? I think there's a lot of progression towards the green hydrogen, and people see this as a future fuels. So a lot of people is accepting that to having like beside their office like a highly pressurized hydrogen cylinder. And also from the bromine side, we are like putting a lot of effort, engineering effort, and we also have like third party to assess the safety of our technology. And because of this all effort, first we score our first commercial agreement with a like a blue chip company called Royal Fopar. So they're like a company that have a lot of knowledge of storing a large amount of petrochemicals, basically. We also have a lot of freedom to operate, especially here in the Netherlands, but also a few parts in Europe, like in Norway, for example, where we also have our project over there. So we get approval in based on our safety analysis. Yeah. And many other projects also already in our pipeline, more than we can handle currently. So in the next 2 years, we are expecting 2 gigawatt hour, yeah, of production of flow battery, and this is like really enough to fulfill and to be like a sustainable company in the short term. Yeah, so finally, just a little bit introduction about Lstore is a relatively young and very multinational company. We see that inclusion as our company culture, and we see that it's important to create to have the best mind from all over the world, just like the best football team in the world. It's normally also consists a lot of nationality. This is also Lstore, yeah, and we also have a lot of in-depth knowledge in like membrane electrode assembly components, and including also the membrane fabrication and the membrane characterization. And we have like cumulatively more than 100,000 R&D hours since 2014. Yeah. And to conclude my talk, yeah, there's a lot of potential and addressable market, both for the flow battery and for the membrane. In the past, we already deployed 50 kilowatt and 250 kilowatt hour, means 5 hour storage time. and we are testing it currently. We also will deploy our commercial product, the first and second, and cumulatively 3 megawatt hours is already signed. And we also letter of intent to upscale this to 250 megawatt hour. And to enable this, we also need to produce our stack and its component also automatically. And 2020-2024, we will construct a pilot plant. And about beyond 2025, this is the interesting word, the gigafactory. We are also looking forward to produce this to address the large market that is available now. Yeah. So I hope you have some idea how big is the electricity storage market, how the Lstore technology can fit into this market, and what is the importance also the membrane technology into our runway into the future. Thank you very much for your attention. Yeah.
All right. Thank you so much, Mr. Hugo. That was a very wonderful and insightful presentation. Hopefully, we'll be able to see it commercialized in the near future. So yeah, if anyone on the audience would like to ask Mr. Hugo any questions about his presentation, we're ready to receive them.
If they ask us later on, Mr. Yohanes, we will definitely contact you, and then we will share with you the questions of our audiences, and then we can get back to them about your answers.
Right. Yeah. And if you have any more interest regarding Mr. Hugo's work at Lstore, you can contact it and check out Lstore's website. Maybe that will help you too.
Yeah, indeed.
Thank you.
So we really thank our guests, Mr. Yohanes and Ms. Begüm, for this really amazing informative presentations that they presented for our energy topic, because as we mentioned during our webinar, this topic is very important in terms of nanofiber technology. So it's a very big part of the market. So this application has a lot of commercialized product availability. So it's offering it,
especially for the future of energy-based applications, which we think it will take a huge toll in the future.
Yeah, indeed. So I think we do not have any further questions. So thanks a lot for joining today's demo. I think we are good now, and we would be happy to welcome you in our next webinar. So thanks a lot for joining. Thank you again, Mr. Yohanes. So we will be definitely get in touch with you about our cooperations as well. So have a wonderful day. Thank you.
Bye-bye.
Bye-bye.